Give me 1 second here. Can everyone see? Thanks a lot, Jordan, and great to see you, everyone, virtually. I think the last time I was there was 2018. Time flies, so I hope everybody is doing well and staying safe. We are, now in the vaccine phase, so hopefully we'll all be meeting in person soon. But great to be here virtually. And today I want to talk about a series of work we've been pursuing at Caltech that I'm very excited about on how to frame new paradigms for learning PDEs. And this is an interdisciplinary effort involving my research group, but also Andrew Stewart and Kaushik Bhattacharya. So Andrew Stewart is a professor in ACM, which is the applied math side of the CMS department at Caltech. Caltech has an interesting mix of both applied math and computer science together, which makes all these collaborations also much more seamless. And Kaushik Bhattacharya has been leading research in the material sciences and the use of PDEs for that. So again, very valuable perspective on what makes the methods practical and usable in many of these scenarios. Great interdisciplinary theme. Jordan talked about our AI for Science effort at Caltech. This is, I think, a great example of that happening in practice. And we'd like to see many more of these close collaborations where, we are deriving deep domain, like we are building on deep domain expertise and knowledge, right? How are traditional methods designed? What inspiration can we take from them, and then combine that with data-driven methods, such as deep learning? What is that right mix and integration, I think, is the key. I mean, that's what makes these things an interesting collaboration, right? Because you can think of AI for Science as, in the beginning, right, you directly applying some existing machine learning methods and looking at the performance. Indeed, that's how you get the baselines. But in most cases, standard machine learning will not be very effective because of the constraints and requirements in many of the scientific applications. most scientific applications you can think of will require some sort of zero shot generalization, right? Meaning generalizing to examples that were never seen during training. For instance, in the case of PDEs, you may have a certain amount of data in some settings of parameters, but then you want to evaluate it under different initial conditions or boundary conditions or different parameters of the PDE, right? So it won't be just in the domain of the data seen. And this is typical, especially if you're making scientific discoveries, you will not be having access to that data at training time. And that's where we need to capture some of the underlying physics or invariants to get to the answer, right? So if you do a standard machine learning approach where the training and test data is assumed to be the same distribution, you won't be getting far with it. And that's the theme I will emphasize, not just with this neural operator project, but also a few other examples that I'll show you on how we can achieve this zero shot generalization. So I would say that's the main takeaway from this talk in terms of designing algorithms where we capture the inductive bias of the domain, the constraints in the domain to enable this zero-shot generalization. So indeed, partial differential equations are at the core foundation of science and engineering. I don't need to motivate that to this audience, right? There is lots of applications from climate modeling to modeling turbulence in fluids, modeling aircrafts, cars, and other aerodynamics in all these settings, designing new materials. So these are aspects that are governed by partial differential equations. So being able to solve them quickly and efficiently is one of immense importance, right? So the way we will frame this task of learning PDEs is learning the solution operator. So this is already where we differ from most of the other works that only learn the solution for an instance of a PDE, right? So you're given one instance of, say, an initial and boundary condition on a certain grid, and you want to map that to the solution, that's an instant, right? Whereas on the other hand, we are saying what you really want to capture for a general purpose solver is the solution operator itself that maps any arbitrary input coefficients, that is, the initial and boundary conditions and other parameters of the PDE family to the output, right, which is the solution. So you should be able to learn this mapping, and that's an operator. Right, so operator extends functions to now infinite dimensional spaces. So the difference is we can use a neural network to map, have the mappings between finite dimensional functions. But then an operator now maps potentially infinite dimensional spaces between input and output. So that's where we need to redesign and think of a new paradigm for operator learning, and that's what we'll call the neural operator. So a lot of that inspiration comes from how we frame solutions for solution operators of PDEs as integral operators. Yeah, so kind of to quickly contrast conventional methods or traditional methods that are not data-driven, right, that use fixed computation to get to the solution. The data-driven methods, in contrast, are learning from certain either empirical data or data generated from existing solvers. And the idea is there's pros and cons to both this, right? So with the conventional methods, you can arbitrarily change any condition, right, and get the answer. But then each time you have to recompute, so it's very expensive. That's why they're extremely slow, especially when you want to get high fidelity solutions. So what makes PDE so challenging is their multi-scale structure. So if you're deriving solutions at a coarse scale, they won't generalize to fine scale, right? You have to do a lot of brute force computation in these traditional methods to get to the solution. That's where, that's why they have been the poster child for supercomputing, right? They require such enormous computational you know hardware. So that's the problem with them, right? Each time you have to recompute, but on the other hand, it's completely generalizable. With the data driven methods, on the other hand, you may end up overfitting to the training data and not being able to generalize. And this brings back to the story of zero shot generalization that I have been emphasizing. Can we learn the solution operator with a limited amount of data? And the benefit of data driven methods is once it is trained, it can be very fast, right? Because neural networks can be compact and small. And also, we have efficient hardware like GPUs to train them and do inference on. So that's what makes it very promising and attractive. But the challenge is we have to first get the data, right? So, and it can also be a boon in cases where you only have the data, you don't have equations, we can apply these data-driven methods we are designing, right? So you don't have an equation at all, you only have data, we can use our operator learning method. Whereas with conventional methods, you have to then figure out what are the parameters of the PDE to fit to the data, and even then it may not be a very good fit, right? So you have to go back and forth. Whereas the benefit with data-driven methods is that you can directly look at directly learn on the data without the need for equations. So those are some pros and cons, but it's very clear that the future is data-driven methods, right? Because of the speed, because of the model-free nature of that, because of the ability to incorporate all kinds of other constraints and information into that. So that's where we are headed now. So let's think about how to go about designing this neural operator. And the main idea, as I said, is to frame this as learning the mapping between input coefficients to output solutions. And these input coefficients can be these initial conditions, boundary conditions, any other parameters, settings for the family of PDE, right? So we will now design a solver for an entire family of PDEs as opposed to just one instance. And that's what differentiates us from all the other machine learning methods for PDEs. They tend to, most of them at least, will look at only one instance of the PDE or learn a new network for each instance of the PDE. On the other hand, we'll have one fixed neural network for the entire family of PDEs and learn the solution operator for that. That's what makes it then amenable to extremely fast evaluation because you train it only once and you can use it as many times as you want on all these different inputs. So that's the benefit of this. And as I mentioned, the main advance is how to generalize the notion of mapping between finite dimensional functions. Typically, you have neural network mapping a vector to another vector, right? Or a matrix or a tensor to another vector, as we see in image classification, but finite dimensional. The difference is we want to learn the operator, which is mapping infinite dimensional functions to infinite dimensional function spaces. And that's the difference, right? So we don't want our neural network training to depend on any particular grid or resolution. It should be able to learn the solution operator between infinite dimensional spaces. And that's the aspect, right? So the data-driven methods we are designing, we wish that to be resolution invariant and mission invariant. So that's the other big difference from other machine learning based methods for PDEs, which are tied to a particular grid or resolution on which the training data is given. But what we argue is then that is overfitting to the training data. What we want to capture is the underlying solution operator, right, for that family, and that should not depend on any particular grid or resolution. So that's the overview of what we set out to do. Any questions? Again, feel free to either interrupt me or even start posting it in the chat, right? And maybe Jordan or somebody could also moderate, and feel free to interrupt me. I'd like this to be interactive. It's always easier in person, but yeah, if you have questions, comments, thoughts, I'd love to know. Great. So it looks like we can proceed. So yeah, the notion of neural operator, what we will see is, similar to a standard neural network, right? You have composition of many linear layers with nonlinearity, right? So sigmas are some nonlinearity. These k are certain linear operations, right? So in a standard neural network, the linear operation is some matrix multiplication with a finite size layer. And then we have nonlinearity like ReLU or other variants. And then we can compose it, and that's what gives us universal approximation for finite dimensional mappings between finite dimensional functions. So the question now is, how do we extend that notion with neural operator to map infinite dimensional functions? And that's where we will see this notion of like a linear operation now will be infinite dimensional, right? So and that's where we will be deriving inspiration from how we can frame the solution operator for PDEs as integral operators. Yeah, to make this more precise, we can put down the problem setting as solving second order elliptic PDE, right? That's the family we have considered so far. You can also go beyond that, but so many popular families are of this form. And what we see here is the mapping from the input coefficients, that is, these are the initial conditions to, or in this case, rather coefficients to the solution. And, you could also more generally have a non-zero boundary condition, right? So that's the more general setting. So that's what we'd like to learn, the operator, right? Going from coefficients to the solutions. And what we know is, the inverse of this differential operator can be written in the form of kernel convolution, right? That's the integral operator. And, for linear PDEs, we are aware that the solution you can write down is in terms of Green's function, right? So if you now convolve the Green's function with this function f here, then you get the solution, right? So that's the way to get the solution for a linear PDE. And then what you can do with nonlinear PDE is now compose several layers of that, right? And that's how we can get a universal approximation then for solution operator of general PDEs. So that's the notion we will use. We'll derive now inspiration from this kernel convolution as the solution operator for linear PDEs. And the goal is then we can now approximate this kernel convolution through a neural network, right? So we want to use a neural network to approximately compute this kernel convolution that is continuous, right? The goal is now we should be able to compute this kernel convolution at any resolution or mesh rather than a very specific mesh or resolution, right? So we want to make it independent and have this continuous convolution. And so that's one aspect. So how do we design a neural network to efficiently compute this kernel convolution? That's one aspect, right? And the second aspect is how do we then compose several layers of that to get solutions for general PDEs. And in fact, stacking several layers of that and using some nonlinearity here, right? We have the intuition that now, this is similar to a neural network, standard neural network between finite dimensional functions, right? You need composition with nonlinearity. And also, right, you can take inspiration from implicit methods in solving PDEs, right? General PDEs. That's also having this kind of an iterative approach of stacking layers. So you can look at it from both the lens, from the lens of what you require for universal approximation is some nonlinear composition, or thinking of it as an implicit method, you need stacking of several layers of this iteration, right? Or several iterations of this convolution, kernel convolution. And so that's the aspect, the main insights that have gone into designing this neural operator. So what we have is now from these Ks are the kernel convolution. So those are linear operators. And now we are composing them with nonlinearity and composing over many layers. So very natural extension of a neural network between finite dimensional functions. One additional aspect, what we can do is we can now learn this solution operator in some lifted space, right? So you can lift it to some higher dimensional space through this linear operation P here, some right neural network layer again, and then you can project it back to the original space. So you can always do that. I mean, this is the standard trick for embedding. And so that's our overall neural operator. So we have now this lifting operation, then kernel convolution, nonlinearity over several layers and projecting it back. And in fact, what we found in our experiments is as little as 4 or 5 layers suffices even for challenging problems like Navier-Stokes, which makes it interesting that they don't have to be very big networks to get even zero-shot generalization to other resolutions, including super resolution. So that's the overall approach. There's indeed now details of how to approximate kernel convolution with neural networks and how to design the right inductive bias that works for these popular families of PDEs. But I want to pause here and take questions because I hope this is the main insight I want to convey, and I hope that has come. Let me go to that. Let me read it. Mm-hmm. Go ahead. Go ahead. I mean, there's always going to be approximation errors, right? As in any standard neural network, right? So, I mean, if you are, looking at methods that are only working at a certain resolution, for sure that doesn't extend, right? But what we said is this framework right now is flexible, right? Because if you can now compute kernel convolution at any resolution, then you're able to evaluate at any resolution. But of course, the performance depends on the setting, right? So yes, if you have a resolution invariant method that works perfectly at all resolutions, then by definition that has captured the solution operator. Uh, but the main thing is the philosophy, right? To begin with, you have to design something resolution invariant if we have any hope of capturing the solution operator. Yeah, right. I'll talk a little bit more about that. So let's postpone that. So so again, right, this, we given this is neural network, right, we cannot guarantee convergence in general, right, because that's the optimization question. And indeed that depends on the family, right? There could be cases where yes, if the complicated subregion, it's hard to resolve, that may get stuck. But we'll see examples like plasticity. I will show you later, where Kaushik, has the expertise. That's where we end up doing multi-scale methods, right? And we'll use the neural operator only at the fine scale and let the standard coarse scale solver use that to resolve. So this need not be right in isolation. You can combine it with existing methods. I think those are great questions, and I agree. We're still in the initial steps of that, right? To assess, and you will see later. I'll show you some results on how well we can capture the invariant measure in chaotic systems, right? So that's again one way to check if we have correctly learned the solution operator, right? Because there is no hope of being able to predict way into the future in a chaotic system. But if we have captured the right invariant measure, right, then we've learned the solution there, solution operator. Yeah, so we need like other kind of surrogate tests like that to assess it. But I don't think we can ever come up with theoretical proofs, right, when neural networks are involved, unless you make some other assumptions. You assume the optimization succeeds or something like that. You'd have to make assumptions, and then you could give more insights into. I mean, the other difference is compared to the right, if we are looking at now for deterministic PDEs here, I mean, not stochastic differential equations, right? There's the issue of generalization is of a different form here, right? In standard machine learning, generalization is about looking at two different stochastic distributions, right? Like training and test are samples drawn from the same stochastic distribution. Whereas here, that's not the notion, right? So there is that difference as well. Yeah, so I would say that in terms of the theory, you will see we have the universal approximation result, but everything beyond is still open. So I think there's lots of room to innovate and think here. Yes, and that's what I'll show you the experimental results. That's the punchline, right? That we are able to do this well. So I gave away the punchline, but that's okay. We'll now. Awesome. Great. So, yeah. So, I hope everyone got this high level now intuition that the way we are framing the neural operator is to lift, right, the input to certain high dimensional space and then do kernel convolution there with nonlinearity over several layers and project it back. And so now the main detail is how to do this kernel convolution efficiently using neural networks, right? What is the way to approximate? And just before that, right, so this is the formal result of being able to extend the universal approximation result now to operators. And what we can show is for any continuous operator on a compact domain, uh, this kind of this framework of neural operator can approximate it. I would say that derivation itself we borrow heavily from previous works. So given that it's somewhat straightforward to come up with this result, and you can see that intuitively too, right? Because you're now doing this kernel convolution at each layer and composing it with nonlinearity. So that should be able to capture any general operator. So, but I will not give the derivation here. So, yeah, so the main aspect now I want to spend time is how to now design a neural network to approximate this kernel convolution. So each layer in this neural network. So, we tried four variants. In fact, the three of them we tried before the one that really worked, the Fourier one, right? They worked reasonably well. So it's not like we arrived at Fourier neural operator right at the scratch, right? We did go through different variations, but the one that has been working wonderfully and has been very exciting is the Fourier neural operator. See, the others intuitively you can, I won't get into the details of the others, but you can intuitively see that, with graphs, you can define neighborhoods and approximate the kernel convolution. You can also do a low rank approximation, right, like PCA. But the Fourier neural operator is the right inductive bias for many popular families of PDEs. And so that's what I will dive deeper into. And later on, I can briefly comment why the other methods don't work as well as the Fourier setting. I mean, the main insight is, the Fourier transform is very well suited for capturing the global convolution. Right. So if you're looking at natural images, these small filters are great because you're only capturing local features, edges, right? Like locally you're capturing them, and that's good. But on the other hand, if you're thinking of like equations like Navier-Stokes, right? There's like global correlation here, like what happens in this region affects region even further away. So that's why the convolutional neural networks with learned filters is not great for the PDE setting. And it's also highly resolution dependent because you're learning filters at a specific resolution, so they won't generalize to other resolutions. On the other hand, with Fourier transform, you can evaluate it at any resolution, you can evaluate it on any grid, and it's also fast, which is another added benefit. So that's what makes this very attractive for neural operators. And also we see that with pseudospectral methods, right? Traditional methods also use Fourier basis. So this is a natural general purpose now for transform for solving many PDE families. So that was the main insight. Now we can compute, or rather approximate this kernel convolution by framing it as Fourier transform. And if you recall, convolution in the Fourier domain becomes multiplication, right? So now you're learning a matrix R to multiply and then do the inverse Fourier transform. So that's now one layer of the, rather, right, one kind of kernel convolution in our neural operator. So very standard here. And that's the other added benefit, because by coming up with this matrix R in the Fourier space, what we can think of this as filtering in the Fourier domain, right? So you are filtering modes, and although we do not explicitly impose any regularization on R, we see in practice it ends up capturing low frequency modes, right? So the idea is, we know in families like Navier-Stokes, right, that there is interaction between different wave numbers and the phenomenon of energy dissipation. So we know that if we can capture only a few of the modes, frequency modes, we are composing with nonlinearity, so we can get the other high frequency modes from low frequency ones. So the network naturally learns that in the Fourier space. And one other detail is, we want to then also add an additional linear transform, because if there are non-periodic boundary and some specific information about the location that may not be very efficiently captured with the Fourier space, right? So it's always beneficial now to also add this additional linear layer here, just to similar to what we see with skip connections, but here there's additional interpretation that if there are highly non-periodic boundary conditions, it's not very efficient to capture them in the Fourier space. So it's better that they are learned through this other transform W and the linear transform directly. So, and we do see that in practice with non-periodic boundary conditions, having this W greatly improves the ability to learn. So some, very simple intuitions and notions to design this. I think the simplicity of it is also its strength, that this can work on a variety of different conditions and is fast and easy to implement. So that's the overall approach here, right? With each layer, we can now approximate this kernel convolution. We can do nonlinearity and then compose them together. Yeah, so what are some experimental results? The details are in the paper. We started with Darcy and Burgers, which are simpler cases compared to the general Navier-Stokes. This is here in 2 dimensions that we are solving. So what you see is being able to train on extremely coarse resolution data, right? So at training time, you only have access to 64 by 64 in spatial resolution and 20 time points in temporal resolution. And then at test time, you can directly evaluate it at a finer resolution. Right, and that's what we see, the ability to do that under different initial conditions, and being able to do that very fast. This is up to 1,000 times faster compared to traditional solvers. So that's what we see, the ability for this zero-shot super resolution and being able to solve under all different initial conditions. And in this case, I believe we had less than 1,000 samples of different initial conditions in this coarse resolution to capture this solution operator. And indeed, we also see that it captures the energy spectrum much more efficiently compared to other methods. We know this, right, about the solution operator of Navier-Stokes. It has this fractional dimension when it comes to the dependence on wave numbers. And what we see is the FNO is our approach, right? You can see that overall it can capture this ground truth pretty well, and also be able to do that at right. So I think the first one is one instance, the other is average. Sorry, that I guess the text didn't display here. And what we see is the ability to also compete very well with other machine learning methods. By the way, all the other machine learning methods here are not capable of zero-shot super resolution. So the training and testing data in this experiment is the same, unlike the one I showed where we evaluated higher resolution. Right. So in that sense, there's not even a competition because the other methods cannot do zero-shot super resolution. But even fixing the resolution, we do see that our method has the lowest relative error on all these variety of settings. And that's where you see that our graph neural network and this multipole graph neural network method and the low rank neural operator, sorry, that's what I meant here. Those variants for kernel convolution don't do as well as the Fourier. So that shows the inductive bias of using the Fourier transform is really powerful for getting good solutions. So that's the thing, right? We are able to compete very well with existing machine learning methods, even on a fixed resolution. And as the added bonus, we can do the super resolution very well in a zero-shot way, which makes this very powerful. And indeed, once we have such a speed up, we can do all sorts of problems which require repeated evaluation of this forward solution, right? And the one such aspect is the Bayesian inverse problem. Here you need to sample for many initial conditions, right? So you need to compute this solution many, many times. And here you see big speed up compared to traditional methods. So we can also now ask, as I mentioned earlier, the ability to capture the invariant measure. And for that case, we started with this simple one-dimensional, I mean, not so simple, right? It's still a chaotic system, but rather simpler one-dimensional KS equation before scaling it up to other more complex PDEs. And the main insight here is, if we can learn the transition, right, kernel here. So, with a small discretization in time, if you can predict what happens in the next time step, and then in order to roll out into the future, you're just composing it many times, right? So meaning you're only training for one-step solution, where one time step discretization, you're learning that mapping, and you're directly now generalizing it to a long time horizon. So we don't expect this to perfectly capture the a specific time trajectory, because anyway, this is a chaotic system, right? It's impossible to predict what's going to happen far into the future given the current time step. But what we hope this will capture is the invariant measure. So if this kind of composition captures the invariant measure, then we've captured the underlying structure of the problem very well. And that's what we see here compared to, you can do standard approaches, right? You can do all kinds of variants of recurrent neural network, which also learns, to map temporally. What we see is the Fourier neural operator for one-step solution. So learning this Fourier neural operator to learn this one-step transition where our training loss is only based on one time step is already very good in capturing the KS equation compared to other models. And we also have, this is ongoing work. We also have results that I'm not displaying here, showing how it can also capture the invariant measure. You can have Wasserstein distance and other kinds of distance measures, autocorrelation functions, all this to evaluate how well we can capture this. And so I think this is very exciting because chaotic systems are inherently not predictable, right? And now what we have is a framework to capture the invariant measure, which is the actual aspect you want to capture, because that's the only thing you can hope to capture in a chaotic system and not the actual trajectories. So the plasticity problem, I think I mentioned earlier, this requires multi-scale modeling. I won't get into the details here, right? This can be extremely complex interactions at different scales. So what we'll do is drop in Fourier neural operator to learn the solution operator at the finer scale and have the standard approach for the coarser scale, right? I mean, ultimately, I believe we can learn end-to-end, like now neural operators at different scales. But to begin with, I think it is always a good approach to ask, can I replace parts of the pipeline with machine learning, and how well does it do? And what we see is right, a visualization of the solution here. And in this case, the neural operator, we even did a simpler, just the low rank neural operator that is for the kernel layer, and composed it with nonlinearity. And this is extremely fast compared to the traditional methods. So that's the benefit we see with speed ups, because the fine scale computation has to be computed lots of times when you're doing this multi-scale approach. Yeah, so the main takeaway here is we proposed this data-driven approach to learn solution operator for families of PDEs. And the main notion is, if we are learning the operator, it should be mesh invariant and resolution invariant, right? So what is the approach to now learn operators between infinite dimensional spaces? And that's the approach of using this continuous kernel convolution composed with nonlinearities. And we see that the Fourier transform gives a great inductive bias to approximate the kernel convolution. And the main aspect is it can produce really promising results on being able to solve complex equations like the Navier-Stokes, and do that with zero-shot super resolution. And so there's lots of future work here to extend this to different families of PDEs, either combine with other solvers, add other kinds of PDE constraints, scale them up. I think this is just the beginning of what we can do here. Yeah, I'm happy to take a few more questions. I had a few other slides of other examples of where we can use the domain constraints, but I'd rather focus on the questions first. And if I have time, I can give a few other examples of projects that also use right, a combination of domain knowledge with machine learning methods. Yeah, so, indeed, right? I mean, why didn't we come up with that first? So we started with graph neural network because we felt that that's a natural method to kind of approximate the continuous convolution, right? Because if you now define a local neighborhood and you compute that locally based on the edges of the graph, then that should be, in theory, able to capture the continuous convolution. So the main challenge there is the sparsity of the graph, right? So for challenging domains like this Navier-Stokes, which is very global convolution, rather global correlations, you need a very dense graph to do that, and that's inefficient. So instead, we propose this deriving inspiration from multipole methods, a multi-level graph neural network, which was certainly better than a flat graph, but still there for computational efficiency, we had to subsample, right? We had to do nice storm sampling, and that really killed performance. I think we did some small scale experiments where we did the brute force full a graph operation, right, on all the nodes, and that was good, but then that's not very scalable. So ultimately, I would say it's the computational efficiency of Fourier transform to capture these global correlations very well. Right. I mean, there's first definitely a threshold, right, in terms of you need at least some minimum resolution for the to capture the right the solution operator. If the resolution is way too coarse, you cannot expect. So, and that depends on the setting, right? And we see this with Navier-Stokes. It's like for that 2D setting, it was 64 by 64. For 3D, it could be something else. We are now experimenting that. So certainly there is a threshold, right? And in terms of like the grid itself, I mean, we've so far done regular grids, but you can define Fourier transform on irregular grids, right? It just kind of the standard FFT implementation won't do. You have to do something more there. So yeah, in principle you can do that, but yeah, that is a bit more complicated. So, yeah, at the moment, we have done it separately for different Reynolds numbers, like a different neural network for different Reynolds numbers. But in principle, we can also give that as one of the inputs, right? That would require like a bigger neural network because you're also having to generalize across Reynolds numbers. So in principle, this should be fine, but we felt for now that was not the most important thing to generalize across. Yeah, I mean, the main one is, I think, because it's learning the solution operator, right? Like if it can resolve it at different resolution, it should also do well at that same resolution, right? They're both related. So I think that's the reason. Right. So, the solvers, the right now we're treating the traditional method as the ground truth, right? So that's because we are deriving training data from that, and then we are testing it. I think we used like the pseudospectral solvers. Yeah, I mean, the thing is, right, yes, indeed, there are approximations even in the traditional methods to get faster solutions. But in the speed, there's no competition, right? These methods are so many orders of magnitude faster. So we felt like that comparison wasn't really necessary. Yeah, so we have been also right like, running experiments with the reservoir computers, computing notions, right? So and all these different variants of recurrent nets, and we see that it's capturing it much more efficiently. But all the experiments are still ongoing, so our results look promising. But yeah, we haven't yet released the details. So we'll when we announce that, we can dig more into it. Certainly, that's what we were doing with the KS equation, right? We were rolling out way into the future while learning only, the small discretization time step. Try, uh, one, that, yeah, learning to predict only on that and then composing that. So I'm not sure what that means, right? Because you can the inverse of the differential operator is an integral operator, so I'm not sure what that means.
Oh, thank you very much. Very interesting talk. And sorry, my question is not optimal for the written form. Um, when you started talking about the approach, you started with an linear elliptic PD, and it makes sense to think of kernels and things operators in terms of kernels. But then you apply it to Navier-Stokes. So am I correct to understand that the nonlinearity is encoded in in the activation functions you use? And the other question I was wondering if you could elaborate on the Darcy simulations. What are exactly the inputs, the training data, basically? I understand it's on a coarse grid, but I want to understand better how you sample the initial conditions. It's a two-part question. Sorry.
Yeah, I mean, the first one, you're exactly right. Right, the main intuition is we are using the non-linearity as a way to extend from linear PDEs to general PDEs, right? And that's also the insight is related to implicit solvers, right? That also have a similar notion of stacking layers, right? So you could think of it from that lens or from the universal approximation lens, right? That you need the non-linearity to do that. So regarding the second one, the details are in the paper, but for all these different Darcy, Burgers, Navier-Stokes, our initial conditions, we sampled it as Gaussian distribution. And our test time as well, we are evaluating it with Gaussian distribution. So I think, yeah, there are some questions there in terms of what if there's a distribution shift also in the initial conditions, right? And we may want to do some kind of domain adaptation methods. So I think there's some nice work to be done. So at the moment, we are expecting the distribution of the train and test in initial conditions to be not that different. I think we did vary a little bit, and right, it was quite robust. But I think more studies need to be done if you want to completely assess the robustness with respect to all initial conditions at all resolutions. But I think the more fruitful approach is that's why to look at capturing the invariant measure, right? Because in a way, if you can showcase that, then you don't have to exhaustively check how it does at all these different conditions. I mean, that's I think this is what I mentioned, right? So, we have to have some kind of threshold on the course mesh being able to capture it faithfully, right? And the main insight here is yes, we have the course mesh during training, but we have many different initial conditions to train on, right? So that's how it's able to capture that, the same solution operator is in work across all these different initial conditions. So it is possible that even with singularities, it could capture it well, or you could use like wavelet transform, which we've also tried out, right? In those extreme cases, maybe that does better than Fourier. Yeah, that's an empirical question. Yeah, I mean, very efficient. Like as I said, like few hundred to thousand samples for even that Navier-Stokes example that I showed. In 2D, and I think as we now scale up to 3D, we will require more than that, but not an enormous lot, right? We are not talking about like billions of examples like in AlphaGo or anything, which I think to me is very interesting that you don't need that kind of. Absolutely. Here we know the solution operator, right? There's extensive research showing that it's finite dimensional, right? I mean, if the operator itself is infinite dimensional, there's no hope that it would be captured well by a small neural network. Yeah. Yeah, we haven't tried it so far, but that should in principle extend well. Yeah, thank you.
Thanks,
Thank you
Anima.
for having me.
Enjoy your weekend.
Yeah, bye. Take care, everyone.